All right. So I suppose the yeah. So the recording has started. All right. Yeah. So there are three people. I think with my experience for in the last past like 2 3 weeks, there are not more than four people who joined. So maybe I think we should get started right away. If anyone has any issue regarding my voice or screen is not visible, my video is not visible or something like that, just let me know. Um, all right, as soon as I said that, the more than I haven't seen more than four people, two people already left. So that's a tragedy. Okay, yeah. uh, okay, maybe I will wait for 3 more minutes. All right. And after 3 minutes, exactly at 6:05, I will start. Okay. Yeah. Okay. So I will just wait for 3 more minutes, and if no one joins, I will get started in. All right. So, Sai Kiran, can you tell me if the screen is visible or not? The screen of the tab. First of all, also let me know if I am audible or not. Okay. So I think this will be what tutorial 5. So everyone, just please let me know if the screen is not visible. Okay, I have shared my screen. If it is not visible, let me know. Okay. Otherwise, I will keep writing, and you guys won't know that I am writing something. So yeah, if the screen is not visible, let me know. Otherwise, I will proceed. Okay. Yeah. I hope so. Since no one is raising their hand or anything, I assume that the screen is visible, and hence I will proceed. Okay. If not, just let me know. Yeah. So you can ask a question either by unmuting yourself. That would be the best way to ask any question. Or you can even write in the chat. However, while look, if I am looking at some question on the screen, I won't be able to see your chats. So it might be better if you can just unmute yourself and ask questions. Okay. So it's 6:05. I think it's a good time to get started. Recording is going on. Yeah. So okay. So yeah. So hello, namaste, and welcome everyone. So this time we will be discussing assignments related to assignment of week 5. All right. In particular, we will be talking about something called dimensionality reduction, and in particular, we will be talking about PCA. This is abbreviation for principal component analysis. Okay. So let me just write it down. Yeah. So this is tutorial 5. Okay. Mainly, the questions would be are on something called principal uh, component analysis. In short, this is also known as PCA. Okay. So yeah. Okay. Yeah. So, okay, so maybe I will. So let me just recap all the things that we have done till now, and maybe through that I can, motivate why something like PCA is important, or in particular why dimensionality reduction is important. Okay. So, till last week, till week 4, we more or less saw the modern feed forward network. Yeah, we saw, how feed forward network works, how you can, learn the weights of a feed forward network and things like that. And it turns out that, these feed forward networks are actually a very powerful tool in deep learning. In particular, the universal approximation theorem, if you remember, is something which guarantees us that, if you have a sufficiently large neural network, you can approximate any function to your desired precision. Okay. So it turns out that feed forward networks are something which is good to have. Okay. However, then we saw something. So then we saw something. So there exists something called curse of dimensionality. So curse of dimensionality. So what is the curse of dimensionality? Curse of dimensionality basically says that, if the dimension of your input space, in particular, if the inputs that you are feeding to your neural network or your feed forward network is of very high dimension, it is difficult to, learn a mapping from this space to, whatever your desired task is. So for example, consider the classification task. Okay. So classification. Okay. You give x some features. Okay. X could be any feature. You are giving it to some neural network. I am not drawing all the connections here, but you can imagine I hope you already know what these connections are. And let's say you have, three classes at the output that you want to predict. So, so ultimately there are three classes. Okay. Three classes. It's a multi-class classification problem. And you need to, so this, whatever this network is, so if f theta is the network, where theta are the weights and all those things. So f theta uh, maps something in, let's say, if the input space x lies in d-dimensional Euclidean space Rd, it has to map it to R3. So R3, right? So because this is in R3. Yeah. So I hope this part is clear. You should be, very comfortable with all these things by now. If you have any doubt or you didn't understand something, let me know, because this is very crucial. Okay. Yeah. So this is the ultimate goal of a feed forward network or neural network in general. However, note that the problem that we observe in general in deep learning is that, if t is much larger than 3. Okay. So imagine that your input features are very high dimensional. It's like they have millions of, parameters in it. So it has millions of features in it, and you are trying to use all those millions of features to, calculate whether which class does this particular sample belong to. So the issue with these things are, there might be, uh, it might be the case that, all these 1 million features are not useful to you. Okay. So it can happen that, there are a lot of redundant features. So let me just write it down. Might might have a lot of redundant features. Yeah. So, so for example, let's take an example of, let's say I want to, uh, buy a house in Bangalore, let's say, okay. Now you have given me a lot of, so for each house I have some features like how many bathrooms does it have, how many kitchens it has, how many, what is the, square feet area of the house and all those things. These are some features that are useful to me, if I have to calculate the price of a house, these are the features that I would, consider to make some assessment. However, let's say, even the area in which the house is located is a feature that I cannot ignore. I mean, so in some area house the price can be high, and at some other area the price can be low. However, consider, someone gives me a feature such as, what could be a redundant feature. For example, let's say, what is the general, uh, okay, so what can be a redundant feature while you are buying a house? Maybe, okay, what is the, how many neighborhoods, so how many people are there in your neighborhood? Okay, so for example, I tell you, okay, for this house there are, five people that live in your neighborhood, or maybe there are three people that live in your neighborhood. Ideally, this feature should not bother you, because you are living in your own house and you don't have to do anything with your neighbors or anything like that. One might consider, I am not saying that, I'm just not able to, figure out some example, so I'm just saying you, giving you an example. Okay, so this can be a redundant feature, I don't need this feature. So one can, argue that if there are redundant features in your input, can't the neural network handle it? The neural network can, assign a zero weight to those redundant features, and it won't consider it at all. Well, if you argue like that, you are completely correct. That is totally possible, and eventually, ideally, it should learn that. However, if you already know that it is a redundant feature, why would you put that additional burden on your neural network, right? You should somehow, you need to be clever, that, you should be clever in the sense that you shouldn't allow your network, you should only give the features that are important to you and not the redundant features. That is what I'm saying. Okay, so in those cases, we need something called dimensionality reduction. Dimensionality reduction. So these are the techniques, which actually, so if your input is in RD, dimensionality reduction algorithm, let's say A is some algorithm, reduction algorithm, it will map it to some RD to RM, where such that, uh, such that M is much less than D. That is all I'm saying. This is a dimensionality reduction technique. Okay. I hope this is clear. I am just revisiting dimensionality reduction, just so that, we are clear, that what is the ultimate goal. Okay, so this was the dimensionality reduction part. Now, having said that, we need to, so you will ask me, okay, fine. The motivation, I hope the motivation at least is clear, that why we need dimensionality reduction. If not, maybe you can unmute yourself and ask some questions. However, so as soon as I motivate you, you will be curious. Okay, fine. So what are the techniques, that one uses to reduce the dimensionality of the input space? So there are several methods. Okay, the answer is, uh, several methods. Okay, several methods slash techniques. After this deep learning stuff has, boosted, there are, like there can be millions of ways to, reduce the dimensionality. Uh, if you are in research in this area, if you are doing research in this area, then maybe you are dealing with it already. However, I won't bother you with those things. I will just, take a shortcut and say that there are several methods. Okay. However, one of the crucial methods that perhaps everyone should know, because it is very simple and elegant, is that of uh, PCA. Okay, what does PCA stand for? PCA stands for something called uh, Principal Component Analysis. Okay, so this is what PCA stands for. Well, I mean this word, this thing, principal component analysis. When you first hear it, it sounds like some big stuff is going on. However, maybe I will give some gist of it. Okay, eventually so nothing is in deep learning, nothing is uh, very high level, or something that you cannot understand. Eventually all the algorithms and all the techniques are trying to say something very simple. However, the language in which it is written is mathematics, and that's why perhaps some people feel that things are very tough and all those things. Okay, so but maybe I will start by giving you some intuition on what PCA is, what principal component analysis is, and perhaps you can so that might help you to get some idea. Okay, so let me just explain it, and maybe if you have some question, you can ask me after that. Okay, so here is the idea. So assume you had something like this. Okay, fine. What I will do is I will create the axis here. So let's say this is the y-axis, this is the x-axis, this is y, and so you have some data points which are here, which are clustered here in some sense. Okay, so yeah, don't let me draw all of them. I will just draw a few of them here. Okay, so we have all these data points. Okay, what I will do is these are data points. Okay, so these are the data points. So you were so you had a data set which was something like this was D1, D2, D3 till some D capital N, where there are n data points. Okay, and each of the DI was something like xi1, xi2. Okay, so it was each of the data points had two dimensions. Okay, so this may be this x1, and this is your second component x2. You can think of it from that way. Okay, now someone comes to you and says that, okay, you know two dimension two dimensions are big. So R2, someone comes and says that this space of R2 is very big for me. I don't have the compute power or computational capability to uh, train a neural network on this. Okay, someone comes to you and just says this. Okay, so well, now you are in trouble. Okay, the that you had some data point. This you had this data point. Now, how can give something to this guy that has come to you, which has a dimension which is less than two, and still he's able to accomplish the required learning algorithm? How can one do that? So that is a valid question, and people often stumble across it. Uh, but what PCA tells you is that, okay, uh, so PCA, what it does essentially is that it says that, okay, look at the principal components. Okay, what does principal component mean? Well, loosely speaking, the direction of the maximum variance are the principal components. Okay, maybe I will just write it down. Uh, so what are principal components? Principal components. What are they? They are nothing but uh, directions with maximum variance. Well, I mean, it sounds very simple, but how do you visualize it? Okay, I mean, I plotted all this, so you could ask me, okay, what is the principal component in this figure? Okay, so the answer would be very simple. So as you can see, which is the direction that has the maximum variance? I hope you can see, this direction has this much variance. Okay, whereas this direction has this much variance. Okay, this direction has this much variance. By variance, I'm just taking, kind of the diameters, or I'm just connecting the endpoints. Okay, this direction has this much variance, right? And similarly, okay. So which one of these has the maximum length? Well, I hope you can see that, this is just an ellipse. Okay, so the largest distance between 2 points in an ellipse is that of uh, this major axis. Okay, so this is the sort of, you know maximum variance direction. Okay, so what PCS tells you is that, okay, so maybe I will draw that. So this blue line, this is the direction of maximum variance. Okay, so this is what your principal component is going to be. And then it tells you that, okay, do nothing, just project all these. So you have all these data points here, right? This and all these data points. What you do is just take this data point, let's say this one, and project it on this. Okay, similarly take this, take project it onto this, project this to onto this. Similarly do it with all the data points. This is what principal component tells you. So that is what PCA is, end of the day. So this was, a visual sort of way to understand what PCA is doing under the hood. Okay. So one way to, so I won't go into the mathematics, as we will, then have very less time. But uh, basically speaking, in some sense, principal component captures the maximum information that is present in your data. Okay. So this was your first principal component. If someone comes and tells you, okay, I mean, if you ask me, okay, this was the first component, then what is the second principal component? Well, if you have seen the lectures, I hope you will agree that, this thing that I drew here, this line will be the second principal component. Okay. uh, why? Because, I hope, I don't, if you saw the lectures, eigenvectors and stuffs. So this is the second eigenvector that will come out of your data point. And yeah, so this will be the sort of the second principal component that you will get. Okay. Okay. So having said this, I will now come to, the tools that you need to, solve your assignments. You actually needed to solve your assignments. So the first thing perhaps is something called eigen value decomposition. Okay. Okay. So what is the eigenvalue decomposition? Eigenvalue decomposition simply says that, if x, if you have a matrix X, okay, which is square. Okay. So one way to, mention that this matrix is a square matrix is just mention the dimension of it. So n cross n, its height and width are same, which is equal to n. This is another way to mention that, it is a square matrix. So any such matrix can be decomposed into three matrices. The first one is something called V. Okay. The second is lambda. So this is the capital lambda. And third one is V inverse. Okay. So what are these vectors? So what is V and what? So I hope you see that there are two matrices. One is V. The second matrix is lambda. Okay. If you know these three matrix, you can, construct your X matrix. That is what this eigenvalue decomposition tells you. But uh, if you think about it, so let me just tell you what these vectors are first, okay? So V is again a matrix, okay? So V1, so I am just writing the columns of V, okay, till Vn. So this is a matrix which is again n cross n, okay? And lambda is again a diagonal matrix. Diagonal matrix means that it has non-zero values only on diagonal, and rest of it is just zero, okay? So lambda 1, lambda 2 till some lambda n, okay? So this is all zero, this is all zeros, okay? So this is again a n cross n matrix, okay? So I hope you can see that, the matrix multiplication of the dimension of this vector is also n cross n. I hope you can see that, because this is n cross n, this is n cross n, this is also n cross n. So the matrix multiplication of all these three matrix will also be n cross n. Okay. So having said this, uh, so okay, I told you all this thing, but I didn't tell you what lambda one, lambda two, v1, v2 are. Okay, so let me just tell that. So these vi's, okay, vi are eigenvectors, okay, eigenvectors, and this lambda one, lambda two, lambda n, or in short lambda I, are eigenvalues, eigenvalues. Okay, so what are eigenvectors and eigenvalues? I hope you remember that if A is a matrix, okay, and it has a eigenvector, let's say x, then ax will be a vector again, okay. So if it is n cross n and this is n cross 1, this will go out and this will become n cross 1 vector, okay. This will be a vector, but this is again x, but just not just x, a scaled version of x, which is lambda x, okay. So this is what eigenvectors are. I hope you remember this thing, okay. uh, so what this eventually what it is saying is that, uh, so let's say this x matrix, okay. So I will just make it here. So X is a n cross n matrix. Okay. So you calculate all of its eigenvectors. Okay. So you calculate all of its eigenvalues. So let's say it has a eigenvalue lambda one, lambda two till lambda n, and for each eigenvalue it will have a corresponding eigenvector. Okay. So this lambda one will have eigenvector v1. This will have v2 till this will have vn. So this algorithm. So this eigenvalue decomposition is saying you that, okay, collect all these v1s and v2 till vn, okay, collect all these lambda 1, lambda 2, lambda n, and construct these matrices, just construct these matrices. And you know if you have constructed this matrix, this decomposition, this decomposition, what, so this matrix multiplication will give you the original matrix x. That is all this is saying, okay. uh, I hope this is clear. This is just basic eigenvalue decomposition that I am sort of recapitulating here. Okay. So the second thing that is required for us to, solve these problems would be something called uh, uh, yeah, singular value decomposition. Singular value decomposition. Uh, yeah. Okay. So what does singular value decomposition tell you? It tells you that, okay, again take a matrix X, but now you don't have any restriction that, it should be square or something, okay. It can be any matrix of any, height and breadth, okay. So it could be a general n cross n matrix, okay. We don't have to specify that, is it a square matrix or is it a rectangular matrix, a tall matrix or a fat matrix or anything like that. It can be any matrix of any required uh, dimension, okay. Then the singular value decomposition tells you that, well, you can decompose this matrix into the following form, which is U sigma V transpose. Okay. So again, a lot of stuff. Okay. Again, well, now you will ask me. So notice that now you have three matrices to work with. Eigenvalue decomposition just require two matrices, V and lambda. This singular value decomposition asks you for three matrices, which is U, sigma, and V. So this is U. You have a sigma, and you have a V. Okay. What are each of them? Again, the question comes. So I won't go into very detail, but let me give you a tricky answer. So this is X. Okay, let's see what is X transpose. Okay, so so another property here is that U and V, both of them are orthogonal matrices. Okay, orthogonal. What does orthogonality mean? Orthogonality means that if a matrix is A is orthogonal, it means that A transpose A is equal to identity, or A inverse is equal to A transpose. So if a matrix has its transpose as its inverse, then it is called orthogonal. Okay, and sigma is a diagonal matrix. Okay, diagonal. So it has values only on on its diagonal, but it doesn't have any uh, values outside its diagonal. Okay, so the non-diagonal elements are zero. All right. So again, one thing that anyone gives you this any kind of decomposition, first thing that you should verify is what are the dimension of each of its matrix. Okay. So U is there, sigma is there, and V transpose is there. Okay. So U has a dimension of, let's say, n cross m. Okay. Sigma has a dimension of m cross n, and V transpose has a dimension of m cross. Uh, yeah, it has a dimension of. Uh, am I missing something? Um, I think that this can be anything. Okay, so it need not be m. This could be n cross r. So r is any other scalar. This can be r cross r, and this should be r cross m. Okay. So I hope you will agree that the overall dimension of the matrix multiplication will these things will club out. These things will club out. This will have a dimension of n cross r, and this has a dimension of r cross m. Now these things will club, and this will become n. Sorry, this will become n cross n. So the dimension matches. This is n cross n. This is n cross n. So we are happy. There is no mismatch in dimension. Okay. This is an important check. Anytime you have matrices, just check if the dimensions are matching or not. Okay. Yeah, so I was saying that what are U, V, and sigma and all those things. Okay, so one way to check this is I will use a shortcut, of course, but if you want to see it in detail, maybe you can watch the lecture, or there are many multiple resources for this. So if X is your matrix, calculate X transpose. Okay, so I know that X has this value. Okay, U sigma V transpose. So I will use it. So U sigma V transpose is there, and I have to take X transpose. So U sigma V transpose again, but transpose of it. Okay. Now, one thing that you should always remember is that if A, B are two matrices and you are multiplying them, the transpose of it will change the order of it. Okay. So this is an identity that perhaps you should remember, that AB transpose is equal to B transpose into A transpose. Okay. Okay, so what will this become? U sigma V transpose, and I will have to take V transpose transpose. So I hope that you will agree that this will just become V, and you will have sigma transpose and U transpose. Okay, this is what you will get. I hope there is no issue here. So now V transpose V is coming here. Okay, U sigma. You have a V transpose V here, sigma transpose and U transpose. Now remember that U and V were orthogonal matrices. Okay, so V transpose and V. So V transpose is actually equal to V inverse. And what will be V inverse into V? It will be identity. Okay, So this thing will become I, identity I, and identity multiplying with identity won't do anything. So this will simply become U sigma, sigma transpose, U transpose. Now again remember that U transpose is equal to U inverse. Why? Again by the same property that I mentioned here, orthogonality. So what will this become? U sigma sigma transpose U inverse. Okay. Well, now your antenna should ring some bell. Okay. Why? Because you have seen something like this. Why? Earlier we saw something called eigenvalue decomposition, which was V lambda V inverse. Okay. I can see something which is looking, so this is matching, instead of V, I have a U here. Instead of V inverse, I have U inverse here. So that is also matching. And instead of lambda, I have a bigger matrix which is like sigma sigma transpose. Okay. So this is what? This is nothing but eigenvalue decomposition. I hope your bells are ringing, right? So what does this tell you? And we know that this matrix B, so what we saw earlier, this matrix B was actually eigenvectors of X, right? So what does this tell you? Okay. So this will tell you that, this tells us what? That you are eigenvector matrix of X transpose, right? I hope you can see that, it's an important thing. I hope you can see that. So we know what U is. Similarly, what else we can say? That, sigma sigma transpose are eigenvalue values of X transpose. So please let me know if this is not clear, but this is a simple trick, just to show that, U is actually eigenvector matrix of X transpose. Okay. Similarly, if you take, instead of taking X transpose, if you take X transpose X, okay, X transpose X, what will that be? So you will have to, reverse the order of these multiplications. So let me just do that. U sigma V transpose into U sigma V transpose. This will become V sigma transpose U sigma V transpose. Now again we have U transpose U. So as we had V transpose V here, which became identity, U transpose U will also become identity. Why? Because U is again orthogonal. Okay. So this will become V sigma transpose sigma times V transpose. And now again we know that V transpose is nothing but V inverse. Okay. V sigma transpose sigma V inverse. Well, again, again the ring should be bell, the bell should be ringing. Why? Because this form is similar to that of eigenvalue decomposition. Okay, so what you can say now? Well, you can say that V is eigenvector matrix of what? X transpose X. Okay, and sigma transpose sigma are eigenvalues of X transpose X. I hope you can see that. Now I also, since sigma is just a diagonal matrix, this matrix and this matrix are the same. Okay, because it's like you are just taking square of the diagonal elements. You do either sigma sigma transfer, or you do sigma transpose sigma. Both will give you square of the diagonals, because sigma is a diagonal matrix. So this also tells us that eigenvalues of X transpose and eigenvalues of X transpose X are the same. Okay, this is another fact that might come handy in future. Okay, so okay, so let me just summarize what we saw. You had U, you had V, and you had sigma. So what is U? So I will just write E vectors of X transpose. These are E vectors of X transpose X. These are E values of either so X transpose X or X transpose. So it really doesn't matter. You can take any one of them. Okay. Okay. So Any questions till now? Because after this, I will start doing assignment questions. Okay. So let me just bring some water. If you have any questions, maybe you can ask. So this is the part of the session where if you had faced any doubt or anything like that, you could ask them. Otherwise, rest of the part, you mostly have the solutions of the assignments. I will just thoroughly explain them. But if you have any question, conceptual doubt, this is the part where you should ask them. Okay. Okay. So no questions. All right. So okay. So I still didn't tell you that okay, I did all this Ramayana and Mahabharata of telling you singular value decomposition and eigenvalue decomposition, but how does it relate to PCA? Well, let me answer that question now. So here it goes. So in PCA, I will tell you what we do. So let's say you have data points which are, let's say x1. Uh, so you have your data set actually, which is x1, x2 till what xn. Okay. What you do is you calculate your something called mean of the data. Okay. What is the mean of the data? Mean of the data is nothing but x1 plus x2 plus till xn divided by. So this is your mean. Okay. In short, this is summation xi by n. Okay. So why is the mean of the data? I hope it is clear from the expression itself, because we are adding them up and taking their average. So this is why we call it mean of the data. Then what you do, so this is the first step. Then what you do is you shift and scale of your all of your uh, so you scale and shift all your data points. Okay. So what does that mean? It means the following. You calculate something called x1 bar, which is equal to x1 minus mu. Okay. You calculate something called x2 bar. What is it? This is nothing but x2 minus mu. Similarly, you calculate xn bar, which is xn minus mu. So I hope you can see that what we are doing is we are just subtracting some constant. Okay. I hope you can see that this is a constant. Okay. This value won't change. Okay. So you are uh, subtracting a constant from each of your data points, and that constant is same, which is the mean of the data. Okay. So this is what we call as centering. Okay. Centering of data. So what? So there was a average. Okay. So there was some data which was spread across. I don't know what. But now you calculated its mean, and now you are saying that okay, every data point should come closer to this mean. Okay. Just so you are just subtracting it and making it come near the mean. Okay. Okay. So now third thing that you do is calculate your covariance matrix, which is denoted by sigma. Was so okay. This is not the summation. This is just sigma. Okay. What is it? It is nothing but this thing. Okay. Okay. Summation. Okay. It might confuse you if I use two sigmas. So I will just write it. Okay. Okay. So you have calculated these x1 bar, x2 bar, x3 bar till xn bar. Okay. So do this x1 bar transpose x1. Okay. Plus x2 bar transpose x2 plus till xn bar transpose xn. So what you are doing is, so this is what is this? This is what x1 minus mu trans. Okay, I think I did some mistake. I did a blunder. What did I do? Uh, this was not this. So it was x1 bar x1 bar transpose. So okay, I will just write it down first. X2 bar transpose till xn bar transpose. So how did I know that I did a blunder? I don't know, man. I don't think any one of you will speak up, but nonetheless, I will tell you. Okay. So, what is the problem if I use x1? Okay, x1 bar transpose x1, or this would be equal to x1 minus mu transpose x1 minus mu, right? And remember that this is a vector, let's say some n cross 1. So the transpose of it will be something called 1 cross, and this will be something cross n cross 1. Okay. What would the multiplication of these two will be? This will be a 1 cross some, whatever this is, it will be a 1 cross 1 scalar. Okay. I hope you can see that. And that was the problem, because I know that it shouldn't be a scalar that I should be getting, it should be a matrix. Okay, so that is why as soon as I wrote this and I was proceeding forward, I immediately saw that okay, this is a scalar I am working with, not a matrix. So that is why I said that whenever you are working with matrices, just be just keep your mind open, and make sure that all of its uh, all the dimensions are perfectly matching. In this case, it wasn't, so I immediately said that I did the print. Nonetheless, I will just remove this. Okay, so this is it. Okay, what is the dimension of this? So x1 has a dimension of n cross 1, let's say, and this has a dimension of 1 cross n. So these things will cancel out, this will become a n cross n. So this is a matrix, I hope you can see that each of, so this is a n cross n matrix, this is a n cross n matrix, and these all of them are n cross n matrices. So sum of n cross n matrices is again a n cross n matrix, and we are taking its average in such things. So I hope that you will agree that the dimension of sigma is n cross n. Oh, I shouldn't use n. Should I? Maybe I should use m, something called m. Okay, just because we already used n here. Yeah. So I hope this is clear. Now I have calculated sigma. Okay. Th- what the fourth? Okay. So what to be? This is called something called covariance. Covariance matrix. Okay. Why is it called covariance matrix? Because this is this is something called x I minus mu summation summed over I, and we are taking the average of it. This is what the formula for sigma is. If you remember probability theory and all those stuff, xi minus mu whole square. Okay. This is sigma square. So if you remember those things, maybe you can relate. If not, there's no issue. Okay, just remember that this is called the covariance matrix. Okay, after calculating the covariance matrix, do you should calculate the SVD decomposition of sigma, which is u sigma v transpose. Okay, SVD. Calculate the SVD of it. Okay. Next thing that you do is, I don't know if you. So I think you don't even need SVD. What you can do is you should. What can you do? Okay, should it work? Maybe not. So do the eigenvalue decomposition. That should work. V lambda V inverse. Okay. Take let's say you want to decrease the dimension of your data points from m to, let's say, something p. Okay. Take top p eigen vectors. Okay, so you see the top p eigenvalues and you see the corresponding eigenvectors. Okay, and project the data points which was your xi on these p eigenvectors. So let's say this, if this is a vector. Okay, so let us say this is the p1 and this was your x1. Projection means that you take the component of x1 here. So this thing will become your x1 projected. Let's call it x1 bar. So this was how PCA works. So I hope you can see that it involves calculation of eigenvalues and all those things. Yeah. So I hope I have explained it in sufficient detail. If not, you can ask questions. Okay. Now what I will do is I will start solving the assignment problems. If you face any if you think that I am not making sense or I am doing some issue, I am doing something stupid, just poke me and let me know that you didn't understand something. Okay, so here are the assignment problems. Okay, so this is the first problem. What is it? We have a matrix A. What is it? It is 0 0.1, 0 0.3, 0 0.5, 0 0.3, 0 0.4, 0 0.1, 0 0.6, 0 0.3, and 0 0.4. Oh my god. 3 cross 3 matrix. Okay. So this has a length of 3, height of 3. So this is a 3 cross 3. Okay. Now we are asked, suppose the maximum eigenvalue associated with this matrix is lambda. Okay, so this is some maximum eigenvalue. Which of the following is true? Well, you are given options like is lambda equal to 1, is lambda less than 1, is lambda greater than 1. You can actually, so what I will, maybe I will calculate the eigenvalues for once. Okay, I don't want to because it will be very, uh, it will be very complicated as it is a 3 cross 3 matrix. But okay, I will tell you one thing. Okay, what is it? So I hope you can see that this matrix is designed in such a way that the sum of the columns 0 0.6 plus 0 0.3 plus 0 0.1 is what? 1. 0 0.3 plus 0 0.4 plus 0 0.3 is again 1. Similarly, the sum of these numbers is also equal to 1. Okay, so the columns sum to 1. Okay, now see the rows. Okay, so 0 0.1, 0 0.3, 0 0.5. What is the sum? I hope you can see that, zero point 0.5, zero point 0.8. So this is not equal to 1. Okay, fine. Okay, so the rows won't sum to 1. This is what? Is it equal to 1? 0 0.4, 0 0.3, 0 0.1, zero point 0.4, 0 0.3, zero point 0.7. So this is not equal to 1. And this is also not equal to 1. So whenever you have a matrix whose columns sum to 1, but the rows don't, it is something called, stochastic matrix. Stochastic matrix. Okay, so suppose you have this stochastic matrix, you have been given this stochastic matrix. Okay, I will someone has asked please solve a small example for PCA. So there is one question in the assignment. I will solve that and maybe that will make it more clear. Okay. Yeah, so as I was saying that you are given a matrix whose columns sum to 1 but the rows don't. Such a matrix is called something called stochastic matrix. So why do we bother? There are some special properties about it, but rather than mentioning it, I will show you. Okay. So let me again write this down: 0 0.3, 0 0.5, 0 0.3, 0 0.4, 0 0.1, 0 0.6, 0 0.3, 0 0.4. And let us say that you are multiplying it with some matrix some vector x1, x2, x3, which has these three elements. So what will this become? So I hope you remember the matrix multiplication with a vector. Okay, so this will be 0 0.1 x1 plus uh, 0 0.3 x2. Okay, plus uh, what? Uh, okay, fine. So 0 0.5 x3. Okay, is there something wrong that I'm doing? Um, okay, no, I think I'm not doing anything wrong. So ax, should I? I'm just thinking of something. Give me a second, okay? So, uh, okay. So I think. it is not a great idea to work with a. Okay. So what I will do is I won't work with A. So I will invoke some. So okay. So let me just tell you what I'm thinking. Okay, I was thinking, that since the sum of these columns, all of these columns are one, maybe while I am doing some matrix vector multiplication, I can get benefit of it. However, when I wrote it down, this was not simplifying because there were no terms to simplify. So I will invoke some property. Okay, I will. So I have some knowledge about linear algebra. I will invoke some properties that I know from there. So what is that property? So maybe I will mention this. So there is a property. Okay. What is that property? Eigen Eigenvalues. Okay. Eigenvalues of any matrix A and A transpose are equal. Okay. Uh, I don't know if this is very evident or not, but this is indeed the case that you take a matrix A, calculate its eigenvalues, transpose the matrix, and again calculate its eigenvalues. Both these eigenvalues will be the same. So maybe you can see it. I don't know. So if Ax is equal to lambda x, okay, uh, you take transpose on both the sides, okay, right? So I am taking transpose on both the sides. What will this become? So this will become x transpose A transpose, right? And this is what x transpose lambda, because lambda is again a scalar, so we won't bother about it. Okay, so this has become something. Now can I use it to uh, now what can I do? I was thinking that maybe I could do something easy and prove it. uh, is there any way to prove this thing on the spot? mm. Okay, so for now, maybe just take my word for it. I don't remember the proof, but I think it's a simple proof. Okay, I don't exactly remember how to prove it, but it's a simple thing. I don't remember. X is equal to some lambda one x, and A transpose y is equal to some lambda two y. What I can do is I can take the transpose here. So this will become y transpose A is equal to lambda two y transpose, and then can I do something? Uh, I can multiply both sides with y transpose. So this will become y transpose. This y transpose A I know is lambda 2 y transpose. Okay, so yeah, so I found the solution as proof. Okay, so it was a simple proof as I said. Okay, so here is the proof of this. Okay, I will just write it down. If I know that I'm deviating a lot, but it's good thing to just having these things in mind. Okay, so here is the proof. So suppose A has eigenvalue lambda one. So okay, so Ax is equal to lambda one x. Okay, x is the eigenvector, lambda one is the eigenvalue. Okay. Similarly, A transpose has, let's say, another eigenvector y, okay, and it has another eigenvalue which is lambda 2, okay, lambda 2y. Now, what I can do is I can take transpose on both sides of the second equation, okay. What will this become? This will become y transpose A equal to lambda 2 y transpose, right? So this, I hope this is this is easy to understand. What I will do here is multiply both the sides of the first equation, this equation, by y transpose on the both side. Okay. So what I'm saying is that do this. Y transpose Ax is equal to lambda 1 y transpose x. I hope you can see that since lambda 1 is a scalar, I can manipulate it. I don't need to multiply a vector with lambda 1. Okay, so this is what it will become. However, this part of this expression y transpose A, I know that this expression is equal to lambda 2 y transpose, okay, from this following. Okay, so use this to substitute here. What will this become? Lambda 2 y transpose x is equal to lambda 1 y transpose x. This is what it becomes. And we know that y transpose x is a scalar and this is again a scalar. So these will cancel out and it will become lambda 2 is equal to lambda 1. So I hope you can see that lambda 2 was eigenvector of A transpose, lambda 1 was eigenvector of A, and we have proved that both of them are same. So instead of working with A, I can work with A transpose. There is no issue. So what I will, instead of calculating the eigenvalues of A, I will calculate the eigenvalues of A transpose, right? So what will be A transpose then? So A transpose will be equal to what? So I will just take the transpose of the given matrix 0 0.3, 0 0.6, 0 0.3, 0 0.4, 0 0.3, 0 0.5, 0 0.1, 0 0.4. Okay. Now I will multiply it with some matrix X. Okay. Which is x1, x2, x3. Okay. What will this become now? uh, will I be able to do anything? X1 plus 0 0.3, x2 plus 0 0.6, x3. Okay. Uh, need to I needed my thing to happen like this. Uh, this is not coming out exactly as I thought. Hmm. Yeah, there's some issue with it. Why am I not able to do it? Am I doing some mistake? 0.1 x1 plus 0.3 x1 plus 0.6 x3. This is correct. I wanted this to somehow be 0.1 x1 plus 0.3 x1 plus 0.6 x1 so that it becomes 1 x1. I wanted to do something like that, but it is not coming out to be that way. Why? I am not sure why. Okay. So what I can do? What can I do? Should no, again I will face that issue there. Oh, so what will the second vector? Uh, had it worked if I did that thing? No, that would have not worked either. Okay, so maybe so sorry, I don't remember the shortcut. Maybe you will have to do the entire matrix multiplication and see. So just delete it. So okay, so maybe I will just mention this. Okay, that uh, max eigen value of a stochastic matrix is 1. Okay. So I'm sorry, I don't remember exactly the proof of it. Okay. Uh, yeah. But you can always do this matrix multiplication. You can always do this thing with a minus lambda I. You can solve for the mod of it and all those things. But I hope that there would be some simple shortcut to do it, but nonetheless, I'm not able to recall it. By the end of this lecture, if I recall it, maybe I will tell you. But for the time being, I don't remember it. So maybe we can look at the second question. Maybe if I remember that, I will let you know. Okay. So sorry for this, but this is a property that maybe you should remember because it comes in handy, especially in the MCQ type of questions where you have less time. If you know such results, you can directly write the answer. Okay. 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 So we have a second question. We have a matrix A which has U sigma V transpose as its SVT decomposition. We are asked that which of the following is always true. So the first option is U transpose U is equal to I. There's a B option which says V transpose V is equal to V. There is a C option which says U transpose U is equal to V. And there is a D option which says V transpose V is equal to 0. Oh, well, this is very easy. We know that, U and V are orthogonal matrices. Okay, what does it mean? It means that U transpose U will be equal to I and V transpose V is equal to I. The transpose are the inverse of the matrices. So this option is correct because this is the property of orthogonal matrix. V transpose V should be equal to I, but I is need not be equal to V, right? So what I'm saying that this thing is equal to I, but V need not be equal to I. So this need not be correct. So B is wrong. C is saying that U transpose U is equal to V. Now we know that U transpose U, this thing is equal to I. Again, I is not need not be equal to V, right? We know this. So again, this is not the correct option. Similarly, we know that V transpose V will be equal to I, but I is not equal to 0. So this is also an incorrect option. Okay. So the second option is, so only the first option is correct. Okay. So let us look at the third question. What is the third question? Third question says that the eigenvalues of A are 2 comma 3. Which of the following are the eigenvalues of A square? A square, okay. Uh, okay, so this is again a simple thing. I mean, it might look very difficult, but here is the thing, okay. So lambda of A, this is for E values, okay, eigenvalues of A are 2 comma 3, okay. Which of the following are eigenvalues of A square? Whenever you get questions, go to something that you are familiar with. What are we familiar with? We are familiar with something called eigenvalue decomposition, right? So make use of it. A is equal to V lambda V inverse. We know that, all right? So okay, I am asked something about lambda of A square, right? We are asked what is it, okay? So I hope you remember that lambda in this case will be a diagonal matrix with 2, 3 here, 0, 0, 0. Okay. Now, what will be A square then? Let us see. V lambda V inverse. So I hope this is equal to A into A, right? So I am writing this is A into V lambda V inverse. This is again A. So this is A square eventually. What will this become? This will become V lambda. So V inverse V lambda V inverse. Now, a matrix multiplication of an inverse with itself is equal to, this should be equal to identity, right? So what will this become? V lambda. Okay, sorry. Lam more hiccups. This will become V lambda V inverse. This is V lambda square. Lambda into lambda will be lambda square V inverse. And we know that, what is lambda? Lambda was something called 2003, right? We have to take square of this to, calculate lambda square. What will be the square of it? This will be 4, this will be 0. Just take the square of each of the elements since it is a diagonal element. Remember that it is only possible for a diagonal matrix to, directly square the diagonal elements. If it were a general matrix, you cannot do this. You will have to do the actual matrix multiplication. Okay. And we know that lambda square is again, so this is a familiar form, right? So what does this tell you? Lambda of a square is what? 4 comma 9, right? Because you can see this is again a form which resembles eigenvalue decomposition. In particular, these and these are V acting as, so the eigenvectors haven't changed. Okay, if when I calculated a square, the eigenvectors haven't changed. However, the eigenvalue has changed. How has it changed? It has become lambda square instead of lambda. So lambda was eigenvector of A, lambda square is eigenvector of A square. So 2 and 3 were the original eigenvectors, 4 and 9 will be the new eigenvectors. Okay. So the answer will be 4 comma 9. Okay. If you have any questions, just unmute yourself and ask. Okay. So this was the third question. All right. What is the fourth question now? So the fourth question is something which is looking scary to me, at least. Let me see what it is. If the dominant eigenvalue of matrix A is less than 1 and the eigenvalues are distinct and non-zero, which of the following is true with respect to sequence S given by, okay, this thing, okay. So what are we given? There are eigenvalues of A. We don't know what they are, but we know that they are less than 1 and they are greater than 0. Okay. This has been given to us. This is given to us. Okay. All right. So what? And we are asked that, okay, if I have a sequence which is AX, okay, A square X, okay, A cube X, and so on, where will this sequence, which of the, where will this sequence converge? Okay, what will, so there are some options that are given. So this is S, this is a sequence. We are asked that does S converge to 0, S converge to 1, S converges to maximum value of eigenvalue of A, S grows bigger and never converges to any point, things like that. So let's analyze what it is, okay? So as we just saw, just in the previous question that we saw that, the eigenvalue decomposition of A was V lambda V inverse, okay? Eigenvalue decomposition for A square was what? V lambda square V inverse. And similarly, you can prove that, so let me write it down. So A raised to n, so any power of A can be written as V lambda raised to n V inverse. Okay. So this is a nice property about eigenvectors. It's a very smooth and very good property that if you take the power raised to n, the eigenvalues become get raised to that power. Okay. This is a nice property to have. Okay. How do we use this property now? So okay, so let me write something down. So let us see for the first element. Okay, so Ax. Okay, what is Ax? Ax is, I know that A is V lambda V inverse. Okay, and I have to multiply it with x, and I have to take the magnitude of it. Okay, okay, fine. I took this magnitude. Similarly, I have to see what is A square x. What will be A square x? A square x will be nothing but V lambda square. Remember from the previous result, V inverse x. Okay. What will be A cube x? A cube x will again have something like V lambda cube V inverse x. Okay. And so on. Now what I will do is I can see that, V inverse x is something that is coming repeatedly. Okay. So maybe what I will do is I will, call them something called y. Okay. So let this be V lambda y. Okay. This will again be V lambda square y. This will be V lambda cube y. Okay. And so on. You can write it down. Okay. Now, okay. So what is lambda? Just let us just remember what lambda is. So this was a matrix which has lambda 1 till lambda n here. Okay. What will be lambda square similarly? This will be have something like lambda 1 square, lambda 2 square until lambda n square. Okay. This will be this matrix, and similarly lambda cube will be something like lambda 1 cube, lambda 2 cube till lambda n cube. Okay. Something like this. So this is the thing. Okay. But okay, but now I have to, analyze the magnitude of each of them. So how do I do that? Well, let us look at this thing. Okay, let us look at the first element, v lambda y. Okay, uh, v lambda y. Okay, so what is it? So v lambda y. What will this be? So we remember that this was v1. So these were, we had stacked all the eigen vectors here in the V matrix. Lambda was a matrix we just saw, lambda 1 to lambda n, and we have y1 till, let's say, yn, something like this. Okay, I hope you agree. Let me know if you agree with this or not. Okay, if you have any issues, let me know. So what I'm so okay. Now, if you remember matrix multiplication, so this, what will this lambda be do? This lambda will just scale the first column of the matrix. Okay, the second eigenvector that will be here, that will just scale the second column. Similarly, lambda n will just scale the last column here. What do I mean by this? Actually, you can club these two matrices, the first two matrices, and write something like lambda 1 v1, lambda 2 v2, lambda n vn. Okay, something like this, and then y1, y2 till yn. This is what I was saying. Okay, this is what it is. Okay, now you can again, so I hope you remember all the matrix modes of matrix multiplication. What you can do from now here is, this is a scalar, remember. Okay, this is just a number. You can multiply this it with this entire column. Okay, so what am I saying? Y1 times lambda 1 v1 plus, this is again a scalar number, this is a vector, you can multiply it with this y2 times lambda 2 v2 plus till y3 yn times lambda n vn. So I am assuming that you know how to multiply to matrix and vector in different modes. Okay. So the general mode is, you take the column, you take the row here and column here and multiply. Take this row again, multiply and do it like that. However, there is another way that you can take, instead of taking the row, you take the columns here. Okay, and but individually multiply it with this number. Take this and again individually multiply and so on. Okay, this will be multiplied by this and sum them up like I have did here, like I have done here. Okay, so all right, so from here I know that lambda 1 y1 v1 plus lambda 2 y2 v2 till lambda n yn vn. Okay, this is what you will get. So this was what? This was v lambda y. So I hope if I take lambda square, what will this become? If you have paid us attention, I hope you will agree that this will become lambda 1 square y1 v1 plus lambda 2 square y2 v2 plus till lambda n square yn vn. Similarly, if I take some v lambda raised to n, okay, so nth power of it, what will this become? Lambda 1 raised to n y1 v1 plus lambda 2 raised to n y2 v2 plus till lambda n raised to n yn vn. I hope you can see that. So now, so what are we asked? Okay, so what are we asked? That okay, if I, if I look at this sequence will go to somewhere. What will happen to this sequence? Okay, so let us check. Okay, so as n goes to infinity, we are seeing what will happen at the end. Okay, at infinite time, after infinite time, v lambda raised to n y, what will this become? We need to check the limit n tending to infinity, lambda 1 raised to n y1 v1 till plus lambda n raised to n yn vn. Okay, maybe I should use m here instead of n. Okay, okay, so I if you we are given that lambda 1, lambda 1 until lambda n are all less than 1. So it's a small number, okay? It's like zero point 0.5 or zero point 0.8 or zero point 0.9. We know that, if I take zero point 0.5 raised to 100, it will become very small, right? Because if you take any number less than 1 and increase the power of it, it becomes very small and goes closer to 0. If I take, so I hope you will agree that this will become, so this quantity will go to 0. So all the between quantities will go to 0. This will also go to 0 because these are numbers. So I am saying that these numbers will go to 0, and hence this entire thing will go to 0, because you will this if this goes to 0, right, this will be multiplied by 0. So this is something, this is going to 0, and this is some quantity. Any quantity multiplied with 0 is again 0. So this entire thing is going to 0. Okay, similarly this entire thing is going to 0. Okay, so this is the sum of zeros. Okay, so I hope you will agree that, the if I have a vector which with all of its elements 0. So I was writing, so a raised to n x, this thing is equal to b lambda raised to n y. Okay, and we have seen that, all of its elements are going to 0. So I hope that this will also go to 0. You will agree with me. Okay, so the correct option in this case will be converges to 0. Okay, so this was, a bit more involved, meaning that you had to actually, bring this AX thing into. So there were multiple steps involved. You had to first observe that, this is simple thing that you will have to take the power of the you will just have to take the power of the eigenvalues. Then from here, you had to, come up with this form of uh, writing the matrix multiplication. Okay, and from there you could see that, each of these elements are going to 0, and hence the entire sum will go to 0. Hence the magnitude will also go to 0. So I understand that this was a bit, it is possible that you didn't understand any some part of it, but if you have some issues or anything was not clear, please ask me. Okay, you can just unmute yourself and ask. No, if not, I will move forward. Okay. Okay. So here is the another question, which is the fifth question. But for fifth question, we are given something. Okay. So let me write that down. So I have been given some data points. So someone was asking that, I should give some examples. So here comes the example: x2 0 2, and there is an x3 which is what, 2 0. Pardon, see, 2 0. Yeah. So what does the fifth question say? Fifth question, what is the mean of the given data point? Okay, so this is something that we just saw. What was the mean of any given any data point? So this was just x1 plus x2 plus x3 by 3, right? So this will be 1 by 3 times 1 by 3 times. What will this become? So this is 1 1 plus 0 2 plus 2 0, right? What is this? So 1 by 3 times 1 plus 0 plus 3, this will be 3, and this will also be 3. So this is just 1 comma 1. Okay, so the mean is nothing but 1 comma 1. Okay, so I hope that is a simple thing to do. I hope you don't have any doubt here. If you have, just unmute yourself. Okay, the sixth question. Sixth question is asking you to calculate. So they are denoting this by x bar. Okay. Sixth question is saying that, okay, the covariance matrix C is equal to what? 1 by n summation I equal to 1 to n. Oh, they didn't mention what I is, but okay, I understand their feelings. X minus x bar transpose. Okay. So this is what they are asking us to calculate. Okay. So, okay. So, uh, again, this is simple, right? This is not difficult. So this is what I was, I hope you remember that I said that this is shifting your data points is what this is shifting. So you are shifting it to the mean. Okay, let's see what this does. uh, So what will be x1 minus x1 bar? So x1 is again, x1 is what? 1 1, right? So this is 1 1 minus my this thing is also 1 1, so this will become 0 0. Okay. What will be x2 minus x bar? X2 is given to us to be 0 2. Okay. So this is 0 2 minus 1 1. This will become minus 1 1. Okay. I hope you can. This is easy to see. X3 minus x bar is what? So x3 is, I think, 2 0. Yeah. So this is 2 0 minus 1 1. This will again become minus. So this will become 1 minus 1. Okay. So we have calculated these things. We have to sum all of them. Okay. I have to sum. Oh, I have to multiply it. So I have to multiply it with their transpose as well. Okay. So let me do that. X1 minus x1 bar into x1 minus x1 bar transpose. What will this become? So this is a 0 0 matrix. Transpose will also be 0. So I hope you can see that this is ultimately a matrix which has 0 0 0 and 0. Okay. What will be x2 minus x bar into x2 minus x bar transpose? This is minus 1 1. Okay. And I have to break the transpose, which will be this thing. What will this become? So minus 1 into minus 1 is 1. All right. What will be the second element? Second element will be 1 into minus 1, which is be minus 1. Okay. So am I doing it correctly? Okay. Okay, no, so I did some mistake. So to calculate the second element, I have to multiply minus 1 with 1 here. Okay, so this will become minus 1. Okay, sorry for that. To calculate this element here, I have to take 1 with, multiply 1 with minus 1. This will become minus 1. 1 with 1, this will become 1. So I am just doing simple matrix multiplication here, nothing fancy. Similarly, x3 minus x bar into x3 minus x bar transpose. What will this become? 1 minus 1, 1 minus 1. Okay, so this will be 1, 1 into minus 1 will be minus 1, minus 1 again, and this will be 1. Okay, all right. So now I have collected all of these. Okay, so each of these I have collected, and I have to add them up. So okay, so I will just add them up. So summation of xi minus x bar into xi minus x bar transpose, what will this become? So this will become, I will just add them. So 0 plus 1 is 2. 0 minus 1 is minus 2. Minus 1 is minus 2 again, and 1 plus 1 is 2. Okay. And I have to take 1 by n, which will be 3 here. So 1 by 3 here. This will become what? 2 by 3 minus 2 by 3 minus 2 by 3 and 2 by 3. This is what it will become. So I think 2 by 3 is equal to 0.67, right? So the third option that I see here, so this will become 0.67 minus 0.67 minus 0.67, and this will be 0.67. So this will be my C matrix. Okay. Again, a very easy thing. Okay, just substitute and multiply. So eventually what this question is making us do is, it is just sort of making us do the PCA manually. Okay, so we just so this the first step was, calculating the mean, as I explained earlier. Second was calculating the covariance matrix, and in the third part, uh, you will see, we will again calculate eigenvalue or something. So there is a seventh question. If you have any question at any point, let me know. Okay, so there was some question. Hi, where we find the recording of this? I am uploading it on YouTube. There is a Excel sheet that must be shared with you. Um uh, Maybe you can unmute yourself if you don't know if the Excel sheet is shared or not. This is actually shared. If not, let me know. I will post the YouTube link here. Okay. Nonetheless, so as I said, I am looking at the questions on the screen. I don't know if you have put any chat or not. It would be better if you can unmute yourself and ask question or any doubt. Okay. So here's the seventh question. So what is our C? C has come out to be a nice looking thing. 1 by 3 with 2 on the diagonals and minus 2 on the off diagonal terms. Okay. Okay, fine. This is C. Seventh question asks that what is the maximum eigenvalue of the covariance matrix C? Okay. How do we calculate the eigenvalue? Just remember, if Cx is equal to lambda x, this is the definition of eigenvector and eigenvalue. What would this mean? C minus lambda I times x is equal to 0. This would mean that norm of C minus lambda I should be equal to 0, determinant in other words. Okay. So what is C minus lambda I would be? So, so this is 2 by 3 minus 2 by 3 minus 2 by 3 and 2 by 3 minus lambda I. Will have lambda on the diagonal and 0 on the other off diagonal terms. Okay. So what will this become? This will become 2 by 3 minus lambda minus 2 by 3 minus 2 by 3 2 by 3 minus lambda. Okay. Now I have to take the determinant of it. Okay. So this is C minus lambda I. I have to take the determinant of it. So for determinant, just I will multiply these two, and subtract. I hope you know the basic determinant thing. Okay. So this becomes mod of C minus lambda I. Uh, this thing which will become 2 by 3 minus lambda whole square. I am multiplying these two terms, so both of them are same, so it will become square minus minus 2 by 3 into minus 2 by 3 will become 4 by 9. Okay, this has to be 0. So what does that mean? 2 by 3 minus lambda whole square should be equal to 4 by 9, right? And this is what? 2 by 3 whole square. I know that, right? 2 square 4, 3 square 9, so 4 by 9. This implies that 2 by 3 minus lambda should be equal to plus or minus 2 by 3, right? It can be either. So the square of plus 2 by 3 is also uh, square root of plus 2 by 3. So 2 by 3 square is also 4 by 9, and minus 2 by 3 square is also 4 by 9. So any one of them will. So what will this mean? That lambda would be equal to either 2 by 3 plus 2 by 3 or 2 by 3 minus 2 by 3, right? So I am taking lambda here and taking this here. So the first term will become what? 4 by 3. Second will become lambda is equal to 0. So this is what it becomes, right? So these are the two eigenvalues that we have, okay? Uh, so what is the maximum of them? Max of lambda, this is 4 by 3, right? And is there 4 by 3? Yeah, there is one 4 by 3 option. So that is the correct option, right? If again, I'm again repeating in the again and again, but if you have any doubt, just let me know. Okay, so this is the maximum eigenvalue that we have calculated. Okay, so now we are asked the eighth question. What is it? It is asking us, okay, now I have calculated the eigenvalue. Eighth question is asking me, what is the eigenvector corresponding to this eigenvalue? Okay, so what do I know? I know that if C minus 4 by 3 I into x is equal to 0. So this was our lambda, but I have just substituted the maximum eigenvalue, which is 4 by 3. Okay, so what was C? What was our original covariance matrix? Okay, so this was the following thing, right? This thing here. So I will just take that. Can I copy it? Let me just copy it, and I will erase this thing, whatever this is. I will just paste it. Okay. Some benefit of using a tab is that you can copy paste things quickly. Minus 4 by 3 times 1 0 0 1. Okay, this into x is equal to 0 is what we know. Okay, we remember that we have to find x. Okay, x is the eigenvector, right? So I will do this thing. So this is 2 by 3 minus 2 by 3 minus 2 by 3 2 by 3. Okay, minus this is 4 by 3 0 0 4 by 3, right? uh, what will this become? This is multiplied by x. So I hope you can see that the first element here will become 2 by 3 minus 4 by 3 minus 2 by 3 minus 2 by 3 2 by 3 minus 4 by 3. This times, let's say my x is x1 has two elements x1 and x2, and this should be equal to 0, right? What will this mean? This will mean that 2 by 3 minus 4 by 3, what is it? This is minus 2 by 3. This is already minus 2 by 3, again minus 2 by 3, and the last term will also become minus 2 by 3. Okay, so this into x1 x2 is equal to 0. I can take minus 2 by 3 outside. Okay, minus 2 by 3 outside. This will become 1 1 1 1. Okay, this will become x1 and x2. This is equal to 0. So this I can cancel out because it is anyway equal to 0. So this means that x1 plus x2 will be equal to 0, right? So note that any x1 and x2 value which satisfies this condition, okay, which satisfies this question, this equation, will be a legitimate eigenvector. Okay, so okay, let me write it down. So any vector of form, so if x1 is, let's say, equal to a, x2 should be equal to minus a, right? So any vector of form a comma minus a will be a valid eigenvector, right? So which of these options has this kind of value? So the first one is 0.7, 0.7. So that is wrong. The second option is minus 0.7 and 0.7, right? So if I say this is a, this is equal to minus a. So this is correct, right? The third option is minus 1, 0, which is incorrect. Fourth one is 1 1, but we need 1 minus 1 kind of thing, right? So that is also not correct. So this will be the correct option. Okay, okay, so this was the eighth question. Now we have a ninth question. Okay, what is the ninth question? Ninth question says the data points x1 x2 and x3 are projected on this eigenvector calculated above. Okay, uh okay, fine, right? So after projection, what will be the new coordinate of x2? Okay, so we are also given an hint that so let us say this is our eigenvector that we are using, that we just calculated here, minus 0.7 and 0.7. Okay, and someone has given us that this is 1 by root 2 minus 1 1. Okay, so they have approximated it fine. Now I have, so what was x2? What was x2? Let me just see here. X2 was 0 2. Okay, all right. Okay. So I have to project x2 on V. Okay. So what does it mean? So this is some vector V. This is some vector V. And this is some vector x2. Okay. I have to project it on this thing, right? I hope you can see what I mean by this. So if I project it on this thing, someone is showing. Okay. So if I am projecting on this thing, this is the okay. Let me write this vector that I will get is what is desired. Okay. So I don't know if you know the formula for this, but so let's say this vector is some alpha v. Okay. Why can I say it is alpha v? Because it is in the same direction as v, but it is scaled down, right? So I am saying that okay, that scaling factor is alpha v. Okay. I don't care what it is. Okay, but okay, fine. Now, what will this vector be? So if you remember some preliminary, projects, vector algebra and all those things, what will this be? This will be x2 minus alpha v. Okay, and we know that this makes a 90-degree angle, right? I know that thing. So if the angle between two vectors is 90 degree, then the dot product is 0, right? This is basic vector algebra. So what does that mean? What it means that V transpose. So this is a V vector. V into x2 minus alpha V. This should be equal to 0. Okay. This is what it means. So uh, this transpose time this thing is like taking dot product. Okay, so what does this mean? This means that, okay, this means that okay, alpha times, so let me use this first. Okay, so this means that v transpose x2 should be equal to alpha times v transpose v. This implies that alpha is equal to v transpose x2 upon v transpose v, right? Okay, so okay, so what is v transpose v now? So v transpose v, right? What is it? So we know that this is minus 1 by root 2, 1 by root 2. This is given to us. Uh, okay, so let me just push it around. This is minus 1 by root 2 and 1 by root 2. Okay, I have to do this multiplication. This will become, the first term will become, okay, so minus 1 by root 2 into 1 by root 2 is 1 by 2, and the second term will also become 1 by 2. So this is 1, right? So this is V transpose x2 by 1, which is just V transpose x2. But is it this, what we wanted was this projected value, right? Which was alpha V. So alpha times V will be equal to V transpose x2 times V, right? This is what the projected value will be. And what is it? So we know again that V transpose is what? Minus 1 by root 2, 1 by root 2. This I know. What is x2? X2 is 0, 2. This is 0, 2. Okay, this is also something that I know. And I know that so this is on one thing, scalar. And V is what? V is again our old matrix that we are working with, minus 1 by root 2, 1 by root 2. Okay. So let us do this multiplication. This multiplied by this will be 0. Okay. Plus this will be 2 by root 2. Okay. And this will become minus 1 by root 2, 1 by root 2. Okay. So this will become, so I hope you will know that 2 by root 2, this will become just root 2 into minus 1 by root 2 into 1 by root 2. If I do the multiplication, if I take this inside, this will become the first term will become just minus 1 and the second term will come 1. This is, so this is what the projection will be, minus 1. So is there any option with this answer? So yeah, there is one option with minus 1, 1. So this will be the correct answer. So this is the projection that I was talking about, you know. So we have projected, uh, so maybe do we have time? Yeah, so we have some time. So maybe I will just plot this thing and tell you what actually happened. Okay. So what were the 3 points given to us? X1, X2, and X3, right? So let me just plot those points. Okay. So please bear with me. Okay, it might seem very boring, but this is very interesting actually. If I'm making it seem boring, then it is my fault. Okay. So this was the first point, which was x1. The second point is 0 comma 2, right? So if I extend this axis, there is a 2 point here. So this was your x2, and there is a third point which is 2 comma 0, right? 2 comma 0. So this is your point, this is your third point, which is x3, right? I hope you can see that, you know, all of them lie on the same line. So actually what I can do is I can just take this point, you know, and uh, so I hope you can see that actually these points are not in two dimensions. They are eventually on this line, this single line, right? And these are situated on this point, okay, on this line. So I hope you can see that it is just a illusion that it is in 2D plane. It is actually on a single line. So I can actually reduce one dimension from each of them, right? I hope I am making sense. If not, please ask questions. Okay. And what was this v vector that we came up with? You know, this vector. So what was v? This one, right? So this was a vector which was minus 1, 1, minus 1, 1. Uh, where is minus? So this was minus 1 and this is 1. Okay. Uh, minus 1 by root 2 and So this is some point here, right? Like, so, okay, let me just write. So this was the V vector that we got, okay? I hope you can see that. So V was what? So it was minus 1 by root 2, 1 by root 2, right? So it should be something here, right? Now what we did was, so I hope you can see that, this vector, if I extend this vector, is parallel to this line, okay? And what we did was, okay, we said that, the second point, we projected it here, and it came out to be exactly minus 1 comma 1, which is this point. Similarly, if we had projected x1, it would have come out to be 0, and this would have similarly come out to be some point, perhaps 1 comma minus. So this is the kind of dimensionality reduction that we are actually doing. So eventually what we found was, okay, if I take this line or this line, it doesn't matter because both of them are parallel. And we projected one of the points on this. We could have similarly projected other points as well. And actually we would have gotten a 1D representation of each of them. Okay. So I hope the intuition is clear. This is the crux of, PC or dimensionality reduction. If you didn't understand, or if you have some doubts, please ask me. Don't think that it is a silly question or something like that. It is a simple question actually. I mean, any question is, there are no silly questions. You can have any question and that would be perfectly fine. So I hope this point is clear. Okay. So I hope I have made my point, that eventually PCA is doing something that is visually very simple. Uh,
So,
if not,
yes.
yeah, 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 go on.
Can you please repeat how is it dimensionality reduction?
Right. So, okay. Okay, so, okay, right. I hope, so is this question because, eventually we are still getting one point which has two dimensions in it? Is this why you are asking this question?
Yes, yes.
Okay, yeah. What is your
I
name?
mean, you
Mona. Yeah, so,
point that
sorry.
why we're saying a line is basically you need a maybe is a can be represented by a linear equation, and then we've got just a point which is that why?
Yeah, so you are right. Actually, this can be actually, I can represent it by just some real line, some r. Okay, and I can say that, okay, this is 0. Okay, so this is at a distance, what, root 2 distance from itself, right? So minus root 2, and this is something called root 2, right? I hope you can see that. So this is a, this is not a straight line. It is a straight line, but it is not the usual x-axis kind of thing, right? It is a inclined line, okay? But I can always, assign some value to this, some value to this, and some value to this, and say that, okay, x1 is now 0, x2 is now minus root 2, and x3 is like plus root 2, and this and initially I had two dimensions here. So uh, originally x3 had two dimensions, but now see, I have made it reduced to just one dimension. So is that clear?
Yes, okay.
Yeah. So yeah, a very nice question. So yeah, so this was a nice question. So I hope the question that Mona asked was clear. That she said that, okay, you did all this drama and came up with some vector. Okay, but it is still two dimensionally, right? I mean, it is still has two components, which is minus 1 and 1. Earlier also it had two components, which was 0 and 2. So what have you done? You are not providing me any reduction in dimensionality. But the thing is that you need to change your basis, and like after, so this was the line that you came, you projected everything here. Okay, and now you can say that, okay, this is 0, so this is some minus root 2, and this is some plus root 2. Okay, so now your reduction is, your dimension has reduced, right? So this was, yeah, so it's a valid question always. So yeah, this is again brings me to one of the core ideas of deep learning. Whenever you are seeing some theory, just make sure the whatever you have, someone is telling you at the end, is concurrent with what he was saying, with he or she was saying at the start. Okay, all right. So last question is remaining. What is this question? This question is saying that there you have a matrix A, which is some 10 cross 10 matrix. Okay, all of its entries are real. Okay, how many linearly independent eigenvectors corresponding to real eigenvalues are possible for this matrix? Okay, so if A has some I comma jth element, it is coming from R. Okay, so I hope you will agree that if all the elements in my in my matrix are real, this means that the lambda of A will also be real. All of them will also be real. Okay, but it is asking me something like how many linearly independent eigenvectors can I have and all those things. So first questions that maybe I should ask is whenever so I hope that I will have to solve something like this to get the eigenvalues. Can you tell me how what will be the degree of this I mean, so this will be like something lambda raised to n, a1 lambda raised to n plus a2 lambda raised to n minus 1 plus a3 lambda raised to n minus 2 and till some a n maybe. It will. So I hope you will agree that when I will write this thing, I will get something like this. Okay, can you tell me what the value of n here will be, the maximum value of n that will be here? uh, if it is not clear, maybe I will just tell you. So this is a so this is a 10 cross 10 matrix, right? I cannot draw it, but let me just, so this has some elements here, right? So, so I hope, so this will have a lambda element. This will have a lambda element. When I uh, write this matrix down, this will have a lambda element. I hope you will agree that the highest power of lambda will come when I multiply all these elements, right? If it is not clear, please ask, okay? But if you won't say anything, I won't go further into it. However, the highest power of lambda will come when you multiply all the diagonal elements, because diagonal is like the biggest path in your given matrix, okay? And how many elements are there in the diagonal? So the diagonal will have 10 elements, right? And since it has 10 elements, lambda will get multiplied 10 times, and hence the highest power that you can get here is 10. Okay. So maximum that you can get is 10, but there is a catch here that I will come to it. So any number that is less than 10 will also work. So 10 is there, that will work. There is an option which says 6, that will also work. However, what if this there you have, so identity is like a uh, uh, what do you call it, exception to all of these things. So if you have a identity matrix, right? So all of these are 1, these are 0, okay, and you multiply any vector x with it, okay, so some vector x, what will you get? You will always get a vector x, right? And so what does this mean? That lambda is always equal to 1, right? Here 1 is multiplied, so you can say that, so this was a, this was x, and this coming to be 1 times x, and so 1 is the lambda. So so this matrix has a eigenvalue that is equal to 1. However, any x that I can come up with here will be a eigenvector, right? So there can be any x, right? So in some sense I can use any x that, I mean, I can think of any x and it will come out to be a perfectly valid eigenvector. And I can have as many of them as I want. So there can be infinitely many eigenvectors here, right? In this case, right? So eventually, what are the number of eigenvectors that I can say? So it can have either infinitely many, as in this case, or I can have any number which is less than or equal to 10. So 10 or 6. So these are the correct options. I cannot have 15 because 15, there won't be a power of 15 when I do this, right? I hope you get my point. All right. Okay, so yeah, so I think I have solved all the 10 questions. Uh, yeah, so if you have any questions, please let me know. Okay. Uh, uh, I still don't know how to do this first thing, but I know this property for sure that stochastic matrix, the maximum eigenvalue of a stochastic matrix is one. I don't remember the proof yet. Maybe in the next session I will do it. But yeah, so this is so sorry for that. Apart from this, I hope I have solved all the questions. If you have any questions, you can let me know, or even if you have some feedback, if I missed something or if I didn't explain anything or you want something to be changed in this session, you can let me know that as well. Okay, so yeah, so I will maybe wait for a second or 5 seconds. If you have anything to say, this is a good time to say. Otherwise, we can end the meeting. So maybe you can at least. So first of all, am I audible? Was I audible or not? I don't know. Yeah, so I don't know. Nonetheless, uh, thank you. Okay, audible, fine. Okay, so we will end the meeting here. Okay, if you don't have anything to ask, if you have any suggestions, you can let me know. Okay, the suggestions are always welcome. If you in yeah, so that's all. Okay, yeah, so I think this will be it. I will maybe close the video. Thank you and have a nice evening. Okay, bye. I will end the meeting.